All right, everybody, we're going to begin our next unit on basic laws of matter. So there's a little bit of math in this unit, so pay attention and we'll be good to go. All right, so let's take a look here at our first law, which is the law of conservation of mass. And it states that mass is neither created nor destroyed in a chemical reaction. It is simply conserved. So basically, whatever you start with, you're going to end up with the same amount. All right, so the mass of the reactants always is going to equal the mass of the products. And remember, the reactants are what you start with, and the products are what you end up with. So very simply, mass of the reactants equals the mass of the products. Let's take a look at an example. So our first example here, we have 10 grams of hydrogen and 5 grams of oxygen produce how much water? So our hydrogen and our oxygen are our reactants, and they should equal how much water, which is our product, that we make. So very simply, take 10 grams of hydrogen and you add it to 5 grams of oxygen, add them up, and you end up with 15 grams of water. So again, you start out with 15 grams, you end up with 15 grams. The last thing on here is Anton Lavoisier, who's pictured over there on the right side of your screen. He was a French chemist. He's kind of one of the founders of this law of conservation of mass. Basically, what he was doing in the experiment is he was combining two things, and he kept getting a mass that was less than what he started with. So he had no idea what was going on. Eventually, what he was able to do is he was able to conceal his experiment, and what he found is he was actually losing mass in the form of a gas. So he was able to hold on to that gas and was able to take a mass of the gas at the end, and realize that, hey, yep, I definitely have as much now that I started with. So that's where the law of conservation of mass comes from. All right, the second law that we're going to look at is the law of definite proportions, and it states that a compound is always composed of the same elements in the same proportion by mass, no matter how large or how small the sample. So basically what this means, it doesn't matter if you have 5 grams of water or 5,000 grams of water, it's always going to be composed of H2O in the same ratio, the same percents. So for example, taking a look here at our water is always 11.19% hydrogen and 88.81% oxygen. So again, it does not matter how much you have, you're going to end up with the same percents as long as it's pure water. So the mass of the compound is equal to the sum of the masses of the elements that make up the compound, and the percent mass is the ratio of the mass of each element to the total mass of the compound expressed as a percentage. So here's the equation. So we have percent mass equals mass of element over the mass of the compound and then multiply it by 100. Again, in the law of definite proportions, this is stating that it does not matter how much of something you have. As long as it's composed of the same thing, it's going to equal out to the same percents. All right, so let's take a look at a couple of examples here with the percent by mass equation. So it says calculate the percent by mass of NaCl. So first what I'm going to do is I'm going to break apart the Na and the Cl. And I'm looking up these values and I get them off the periodic table. So on the periodic table, it told me that Na, sodium, is 22.99 grams, and Cl, chlorine, is 35.45 grams. So I'm going to add those two numbers up, and I get a mass of NaCl to be 58.44 grams. So what I'm going to do is I'm going to now calculate a percent by mass of each one of these things. The first one I'm going to do is the sodium. So again, the mass of the element, which is 22.99 grams, I'm going to divide that by the mass of the compound, which was 58.44 grams, and then I'm going to multiply it by 100. So when I solve that out, I get a percent mass of the sodium to be 39.34%. Now I have to do the same thing for the chlorine. So again, mass of the chlorine divided by mass of the compound, multiplied by 100, and I get a mass of 60.66%. Now, obviously, you should be able to add up those percents, and it should equal up to 100% of the compound. So again, it doesn't matter if I have 2 grams of NaCl or 2 billion grams of NaCl. The ratio would be always 39.34% sodium and always 60.66% chlorine. In the second example, what I suggest you do is pause the video, and that way you can try to solve it by yourself. I'm going to go ahead and go through it, but again, make sure you pause the video and try working on this example by yourself. Alright, so now I'm going to calculate the percent by mass of a molecule of water. So I'm going to first start off with the chemical equation for water, which is H2O. And that's something that you guys all should know. So we have hydrogen and we have oxygen. Now we have two hydrogens in the formula, so we have H2, so 1.01 plus 1.01 equals 2.02. And we have one oxygen, so I have 16 grams of that. So add them together and I get 18.02 grams. Now that I have the mass of the compound, I can go ahead and do the percent by mass of each thing. So I'm going to start off by doing the hydrogens. So again, I have H2, all right? So I have to do the 2.02 divided by 18.02, multiplied by 100, and I got 11.21%. I'm going to do the other one, mass of oxygen, 16 divided by 18.02 times 100, and I get 88.79%. So again, the ratio of the water here is 11.21% hydrogens to every 88.79% oxygen. Now, you might be thinking that's a little bit different than what you said on the slide before. And the reason for it is my number that I use off my periodic table for hydrogen is 1.01, whereas another periodic table used 1.008. All right, so let's look at the last law that we have. It's the law of multiple proportions. And it says the law of multiple proportions states that if two or more different compounds are composed of the same elements, then the ratio of the masses of the second element combined with a certain mass of the first element is always a ratio of small whole numbers. All right, so let's take a look at an example for this. So we have carbon monoxide and carbon dioxide, and we end up with a 2-to-1 ratio. What I mean by this is that essentially the oxygens, as you go up, will exist in a 2-to-1 ratio. So if we take a look over here at the little diagram on the right, we can see that we have 1 gram of carbon. And then if we take that 1 gram of carbon and we reduce it to small whole number ratios between the two, you can see essentially we're working on a 2-to-1 ratio between the oxygens. And that's the gist of what the law of multiple proportions means. Don't spend too much time on this. I know it's a little confusing. Just understand that it exists in a small whole number ratio when you can reduce it down.